Holy cow. Okay, so you got the announcements about the test next Monday and the apology that we didn't get further in chapter 6. We're going to talk about functions. We're going to lean in on the idea of a function as a set of ordered pairs. Hey, everybody in here knows what the domain is, right? Everybody's heard of the domain of a function. Well, we're going to talk more about that and probably what you called the range of a function in high school is what's technically known as the codomain. We're going to talk about that and we're going to extract that idea from the actual technical idea of the range. So we'll talk about these definitions. We're going to look at numerous examples with pictures that should help get the concepts flowing. And then we're going to talk about images and inverse images of the domain and codomain. And then in section 7.2, we're going to talk about two really important properties of functions. It's called the onto property and the one-to-one property. So I'd like you just to take a minute right now and think about anything you know about functions. Do you remember anything from prior classes or your experience as a math student about functions? So if you have any thoughts at all, you can just mic in or chat in. And let's see if you remember anything at all about functions. Has anybody ever heard of the vertical line test? Does that ring any bells? The vertical
Yeah,
line test for a function?
yeah.
Yep. So we're gonna break down the definition of a function, and hopefully you can relate that to this idea that if you take the graph of a function, like a picture of a function, and you take a vertical line and you just kind of move it across the plane, that line cannot intersect the picture at more than one point at a time. As you move it, 1 point, 1 point, 1 point. Okay, so we're going to break down the definition of function and we're going to look at the pictures that should help. So here we go. All right, let's just think about probably an old friend of an example from high school. Do you remember this one? Do you remember this notation where we would say f is a function like from the reals to the reals? This notation is reserved for functions, okay? We'll get a formal definition in a minute. But do you remember the squaring function? The function defined by, we would say f of x equals x squared. Remember that one? It's a function that has a graph that's sort of interesting here. I'll draw it over here. It looks like a parabola. It's the classic parabola. And, the x-axis would be going this way, and the y-axis would be going this way. And, a point on that graph would have the form, x for some, x value on this copy of the reals, comma x squared, where the x squared is how high up the point is. That's the y coordinate value. Remember that? Well, the idea of the vertical line test is well demonstrated with this graph. If you just imagine, a vertical line. Okay, I'll just draw one. Here's a vertical line. It's only going to hit that graph at one point. You can move it over. No matter where a vertical line is drawn, it should only touch the graph in one point at a time. So I'd like to think about f as a set of ordered pairs rather than an equation defined idea. So if we think about f as a subset of R cross R, in other words, its elements look like the elements of R cross R because all the elements come from R cross R, but not all of R cross R is it. Not all those elements in R cross R are elements. It's only the ones that we graphed here. So these are ordered pairs. then we can think about F this way. It's a set, and the elements look like ordered pairs, where the first coordinate would be x and the second coordinate would be x squared. And this is such that, or with the property that x is an element of the reals. And of course, if x is an element of the reals, so is x squared, because of closure properties that we all know so well now. It's a subset of R cross R. But not every element in the codomain, which is this copy of R. The first copy of R is the domain. The x's come from the domain. You may have called the second copy of R the codomain, but it's, the range. But maybe you did correctly call it the codomain. It is called the codomain. But we have these coordinates. And if you look, at this picture I've drawn, notice that the negative y values, none of them are achieved by this function, right? So there are elements in this copy of R, the codomain, that don't get, graphed to. They don't get hit. In other words, there is no y that's negative that would equal an x squared for a real x. So there's a real difference between the y values that actually are achieved by x squared for some real x and the set of all the possible y values, kind of like a target that we're shooting at. We don't hit everything in the reals. We only hit the non-negative real numbers as our y coordinates. So just to remind, just in the context of maybe what you might remember, this is called, a domain element, the x. And this x squared lives in the codomain. And we're going to formally define domain and codomain, so don't worry. I'm just trying to kind of set you up in the context of an example you may have seen in high school or more recently. Let me just make sure this is in focus. Is that a little bit better? Is that any better at all? About the same? Okay. Well, here we go. Let's get a definition, folks. We are ready for a definition. Given non-empty sets, x and y. So we don't play empty function games. We have to have non-empty sets, x and y. They're supposed to be big. A function, that's what we're defining, a function f from x to y. So we're defining what it means for an object to be a function from x to y. And it's denoted by, we reserve this kind of notation for functions. We only use this notation if we're talking about functions. So it'd be denoted by f colon x arrows pointing toward y. Okay. And we read this f from x to y is a subset of x cross y. And in the notes that I posted, I put little hands and feet on these x's and y's, so they look a little bit more distinguished. But it's a subset of x crossed with y, satisfying this. For each element, little x, in set big X, there exists exactly one element. We'll call it little y in set big Y, such that the ordered pair little x comma little y is an element of this subset of x cross y that we're calling F. So now we've just defined what it means for it to be a function. Every domain element, every element of x has to pair up with exactly one element of y. Let's get the domain and codomain definitions down. the set X is called the domain of F. And the set Y is called the codomain of F, of course. Also, folks, we write, and this is notation I'm sure you've seen, f of x equals y if the order pair x comma y is an element of F. So I'm trying to tie back in to notation that you're familiar with, but we're actually going to focus on the ordered pair definition of a function. We're going to view a function as a set rather than as a picture of a graph. Okay, a lot of times we think of the picture of the graph as being the function. Well, that's just the graph of the function. The function itself is actually a set of ordered pairs. So geometry and algebra are amazing. Rene Descartes invented the connection. When people were studying algebraic entities like ordered pairs x comma x squared, it was Rene Descartes that had the brilliant idea, wow, maybe we should graph that. Maybe we should make a picture where we plot the points x comma x squared. And sure enough, we now have what's called the Cartesian coordinate plane, right? All right, so we're going to look at one more definition, and then we're going to start chomping on examples, okay? I'm going to keep this definition close by, though. The range. Okay, the range of a function. I'm going to change my letters just so you can get used to having different letters for the domain and the codomain. Given a function f, say, from A to B, big A to big B, these are sets, we define, in fact, when we say that f is a function from A to B, you are to understand that A and B are non-empty sets, okay? And that f is a subset of the cross product. We define the range of f, and it's denoted by R in G of f. We just read that range of f as follows. Okay, and before I write down the definition, I just want to give you the intuition so that you don't feel completely overwhelmed by these definitions. These elements in the range are the elements of B, the codomain, that actually are second coordinates for some x from the domain A. These are the y elements that actually are achieved. So the range of f is equal to the set of y in capital B such that there exists an x in set A where the ordered pair x comma y is in F. So I'll just put a little note here, and I'm going to try to say things as many different ways as possible. Find F. Oh, excuse me. Can't read my own writing. It's supposed to be a range of F. Maybe I should put my glasses back on. The range of F is the set of codomain elements that actually appear as second coordinates of ordered pairs in F. Any questions? right, so shall we look at another example? In fact, we're going to focus on finite examples. This is discrete math is considered finite mathematics. Even though we do play continuous games with the reals, we want finite examples. I said the word mathematics and wrote mathematics. I just meant to say examples. It's okay, it's correct in the notes that are posted. All right, example 2. Here we go. Let's let set A be the set containing the elements 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. And B, just for a little variety, let's say has the elements little a, little b, little c, little d, and little e. So consider this subset of A cross B. Okay. F equals, here we go, open set brackets. First ordered pair is 1, comma A. Close your soft parentheses. You got to use soft parentheses for ordered pairs. Second element is 2, comma B. Third element is 3, comma C. Fourth element is 4, comma little d. And the fifth element is 5, comma little d. So 1, is f a function from A to B? That's my first question. So here I'll put the definition of function where you can see it. So f is a function from A to B. For each x in A, there exists exactly, oh, this should say exactly one element y from B such that x comma y is an element of F. What do you think?
F is a function from A to B.
Okay, I've got a vote for function from A to B. Anybody have a different vote? Well, Edwin's correct. Each element of the domain, namely the elements 1, 2, 3, 4, and 5, they each appear exactly once. That means each, as the first coordinate in an ordered pair in F. And that means each one of them is pairing up, and look at their codomain elements, little a, little b, little c, little d, little d. These are all elements of the codomain B. So this is a function from A to B. It's okay that 4 and 5 both mapped to D. That is not a problem. I mean, look at the parabola. Look at the x squared. If you pick 3 and minus 3 for your x values, when x is 3, x squared is 9. When x is negative 3, x squared is still 9. It's okay for different domain values to map to the same codomain value. That does not bother the definition of functions. So yes, each element of A pairs with exactly one second coordinate, element of B. One second coordinate coming from B. All right. So 2, if f is a function, which it is, but you might get both of these questions at one time, find the range of f. The reason I say if f is a function is because the idea of range of f is meaningless if we're not looking at a function. Okay, so we've got our definition of the range of f right up here. It's the y's and b that actually appear as second coordinates. They're the y's that have an x, and an x exists in A, where xy is in F. So what is the range of F here, folks? You can just scan the set of second coordinates because those are the range values. Right? So little a, little b, little c, and little d. Notice, the set B that is the codomain has an element E that did not appear in the range. That means this particular function does not have a property we're going to learn later called the one-to-one property. Anyway, we'll talk about that in a minute. But we can get an arrow diagram. The arrow diagrams are really helpful. And we have other kinds of diagrams like kind of machine diagrams that we can look at next time, because some people like to view a function as an input-output situation where the input, like the domain, the elements 1, 2, 3, 4, and 5, yield output, and the output would be the elements of the codomain, A, B, C, D, and E. So in the arrow diagram for this particular function f, 1 is mapping to A, so you just draw an arrow from 1 to A. It is called an arrow diagram. So these lines that connect domain elements with codomain elements are directed lines. They do have tips, okay? 2 maps to B. If you just draw a line, you're going to lose a point, right? 3 maps to C, 4 maps to D, and 5 maps to D. So this is okay. It's okay that 2 different domain elements map to the same codomain element. That does not violate the definition of function. All right, let's use the same A and B, and let's look at another subset of A cross B. Any questions before we move on? So in example 3, like I said, we can use the same A and B. 1, 2, 3, 4, and 5. It's nice and simple. B is the set containing little a, little b, little c, little d, and little e. And now it's the same setup. Consider this subset of B cross A. So I'm trying to mix it up a little bit. It's a subset of B cross A. Because once we have 2 sets, we can play the function game in either direction. We're going to call it G. And it's the set of ordered pairs, little a, comma 1, little b, comma 2, little b, comma 3, C 4, D 5, and E 5. Is G a function from B to A? Do we need to see the definition of function while we answer this question?
G isn't a function
Why would you say it's not a function?
because B has a coordinate that goes with 2 and then with 3.
Yeah, there's an element of the domain, namely little b, that's paired up with 2 different partners. It's mapping to 2 and it's mapping to 3. That definitely violates the definition of function. Each element of the domain, there has to exist exactly one element of the codomain that it pairs up with. So the correct answer is no. Of course, you would be asked to justify that. So you could just say something like, since B, little b, is an element of set big B pairs. So since little b and B pairs with two different elements in A, namely 2 and 3, G is not a function from B to A. You know, the problem is happening right here and right there. So one of the other things you can do is, you know, if you draw the arrow diagram, this kind of problem that we're seeing with this copy of F, so little a, little G, excuse me, C, D, E, can be seen in the arrow diagram. I'll show you what happens. Now A's mapping to 1, but look what's happening with B. It's mapping to 2, but then, you know, its arrow splits and also goes to 3. You can't have that. B goes to 4, D goes to 5, E goes to 5. There's no problem with two arrows hitting the same element over an A, but you can't have a splitting arrow. Okay? So that's the problem right here. Okay? Now let's talk about the notion of images and inverse images. These pictures can be helpful for that. These arrow diagrams. So here's a definition. So to play this game, we got to have a function. So given a function, f, from A to B, and subsets C, which is going to be a subset of A, the domain, and D, which is going to be a subset of the codomain B, we define, well, we're going to have two definitions. The first one is the image of C, and it's denoted by, it's the image of C under F, but I'll just say the image of C. It's denoted by F of C. The whole function is F of A, but we're looking at a subset of A called C. So the image of C is called F of C. And the inverse image of D, and it's denoted by F with a superscript -1 of D. Please don't confuse this notation with the notation that you may have seen when you learned about the inverse function for a function. Like, you know, the sine function has an inverse function, namely, right, the cosecant function and that sort of thing. This is a set theoretic inverse, not a functional inverse. So we define both of these as follows. Here we go. F of C is equal to the set, so it's a set containing the y in set B such that there exists an x in C where f of x equals y. So you can think of these as the y's that have arrows pointing to them out of the set C, the subset of A that we're calling C. And F inverse of D is equal to, well, it's also a set, but we're looking backwards to see what mapped into D. So it's the X in A such that F of X is an element of D. In other words, It's the X's in A whose arrows landed in the subset D. Okay, we'll draw some pictures. All right, so let's do an example. We can use the same example we've been using so far pretty much all evening, except for our very first example. So we're going to recall F from A to B, where A is the set containing 1, 2, 3, 4, and 5. B is the set containing little a, little b, little c, little d, little e. And F is the set of ordered pairs. 1 maps to a, 2 maps to little b, 3 maps to little c, 4 maps to little d, and 5 maps to little d. And we're going to let C, big C, be a subset of A, be this set. C is going to be the set containing 1 and 2. And we're going to let D, big D set, be a subset of set B, be this. Set D is the set containing little d, that's all. And then we're going to let H be also a subset of B, be this set. In H, we're going to put the element little e. Okay, so we have a domain and a subset of the domain called C. We have the codomain B and subsets, a couple of subsets of the codomain, D and H. All right, we're going to find each set. First, we're going to find f of C. I'm going to skip a line. Then we're going to find f inverse of D. And then we'll find f inverse of H. Okay? Now, before we try to, find these, I'd like to add a picture here to kind of help you see what's going on. Drew it on the board this afternoon, but added it to the notes later. So there's a little funny message saying Dr. G will add this later. 1, 2, 3, 4, 5. I'm going to put the numbers on the left of the dots so that they don't get in the way of my arrows. Little a, little b, little c, little d, little e, and I'm going to put the letters to the right of the dots so they don't get in the way of the arrows. And 1 maps to A, 2 maps to B. We've already seen 3 maps to C, 4 maps to D, and 5 maps to D. But we're going to add something here. C is the set containing 1 and 2. Okay, so we're going to draw the subset C like it's a Venn diagram here. There's C contained in A. And D is a subset of B that just contains the element little d. So here's the subset of B called D. And H is also a subset of B, and it's the subset that just contains the element E. Okay. This should help us, because when we're looking for f of C, okay, so C has 1 and 2 in it. If you just want to do it algebraically, look where 1 was sent, all right? Look at what 1 is pairing up with, and then look at 2, and look what 2 is pairing up with. It's these second coordinates that, by definition, are f of C. F of C is the set of second coordinates where the first coordinate comes from the set C. All right. So what would be in f of C? This is f of the set containing 1 and 2. So what is going to be f of c, folks. You can see it in the picture, or you can see it with the algebra.
1A and 2B.
It's just going to be the A and the B, because f of c is a set of y coordinates. Let's take one more look at the definition. I'm glad you said that. That's a pretty common misconception. F of c is the y coordinates only, not the whole ordered pairs, okay? So it's just the y coordinates, A and B, or, you know, you can look at it in the picture. It's the arrows coming out of set C hit A and B. Now, F inverse of D is the x coordinates whose arrows land in D. F inverse of D is going to be the first coordinates where the second coordinate is in set D. So if D is the set containing little d, what we're looking for here in the second problem is F inverse of just the singleton set containing the element little d. So we're looking for the x coordinates that pair up with little d. Everybody see that? So what's F inverse of D, folks?
Set of 4 and 5.
Exactly. And if you want, you know, to say a little bit more, why is F of C the set containing A and B? Well, it's because F of 1 is A and F of 2 is B. And why is F inverse of the set D 4 and 5? Well, that's because F of 4 is D and F of 5 is equal to little d, and they're both elements of big D. Okay. What about F inverse of H? Here's H. H is the set that contains E, which is a subset of the codomain. Anybody got
Is it an
any?
empty set?
It is. It's okay for it to be empty. Why is it empty? Because no element from A has its second coordinate. I don't need a parenthesis. I don't need this. Has its second coordinate equal to little e. Or another way to say it was no element from A maps to little e. It's the only element of H. And of course, that's a subset of B. This notation is okay. All right. Any questions? Those are the main concepts that I would like for you to learn from the first section in Chapter 7, definition of a function, the idea of domain, range, and codomain, and the idea of the image or inverse image of a subset of the domain or codomain, respectively. All right, let's learn about properties. We are now going to be in section 7.2, if nobody has any questions. And there are two properties that we want to learn about: the one-to-one and onto properties of function. So let's go ahead and get our definitions right off the bat here. And we're going to try to understand it from as many points of view as we can, including pictures. Given a function, f from A to B, what do we say? We say 1. F is onto, and we're talking about being on to B. We usually just say F is onto, but it's actually onto the codomain B if every element little y in B appears as the image of some element, little x in A. I.e., if you want to think about it in terms of the range, B, which is the codomain, is actually equal to the range of F. Every element of B appears as a second coordinate. That's another way to think about it. Every y in B appears at least once as a second coordinate in F, which of course is a subset of A cross B. Okay. Now, that's on to, but the other game that we're going to play is the one-to-one game. F is 1-to-1 if, and now this definition is an if-then definition. It's an if P then Q definition. Here we go. F of little x1 equaling F of little x2 implies that little x1 is actually equal to little x2. Let's unpack this because that's kind of a confusing definition. It means that if you have these are the y coordinates, right? The F values are the y coordinates. If you have two y coordinates being the same, if they're equal, then the x coordinates actually had to be the same. Here's a picture of a function that is not one-to-one. Remember, if we look at 3 and we look at -3, they both map to 9. So f of 3 equals f of -3, but 3 is not equal to -3. So this is an example of a function that's not one-to-one. And in fact, in the same spirit that we have a vertical line test for a function, there is an equivalent test for one-to-oneness. It's the horizontal line test. If you slide a horizontal line across this graph, there are lots and lots of times when it'll hit the graph twice, more than once. This function is not one-to-one. So we can think about it, in terms of this if-then definition, which is really helpful, especially for trying to prove that F is not one-to-one. Then we want to show that P happened, the hypothesis happened, and the conclusion failed, right? F of -3 equals F of 3, and 3 is not equal to -3, for example. But another way to think about it is that no element Y in the codomain B is the image of more than one X in A. Another way to think about it to try to correspond with this is no Y in B appears more than once as a second coordinate in F, which of course is a subset of A cross B. All right, let's revisit this kind of running example. This example, I'll call it example 5, but it's really example 2 revisited, where A is the set with 1, 2, 3, 4, and 5. You probably have memorized it by now. B is the set containing little a, little b, little c, little d, and little e. And F is the set of ordered pairs where 1 maps to little a, 2 maps to little b, 3 maps to little c, 4 maps to little d, and 5 maps to little d. Okay? Let's just take a look at this. Is this F onto? Here's our definition of onto.
The F isn't on to B.
It's not. Good. F is not onto because there's an element in B that does not appear as a second coordinate for any of the ordered pairs, namely little e, right? So because little e in B, which is the codomain, right? But E is not an element of the range of F, since no element in A pairs with E. So B is not equal to the range of F. Everything has to get hit by an arrow for F to be onto. Is F 1 to 1?
No, because D repeats twice.
That's right. D is the image of both 4 and 5. And for F to be 1 to 1, no element from the codomain can appear more than once as a second coordinate. It's okay for an element to be missing as a second coordinate. You just can't have an element appear more than once as a second coordinate. So F is not it's not 1 to 1. Because F of 4, right, it's P and not Q, right? So F of 4 equals F of 5. Right? They're both equal to D, but 4 is actually not equal to 5. So let me ask you a question. We'll call this example 6. Using the same A and B as in example 5, is it possible to construct a function G from A to B that is both onto and 1 to 1? If so, construct such a function. If not, explain why it's not possible. I'm seeing your chat. I second his, Rania. I enjoy your chat so much. So can we build a one-to-one and onto function from this A to this B?
Yes.
Yeah. And what's kind of the key thing happening? What is it that makes that possible? Do you kind of see what's going on here with these finite sets?
There has to be enough like elements in A. There has to be like no like the same number of elements in A and B for it to be one for one.
That's right. For finite sets, we have to have enough elements in A to hit all the elements in B with their arrows. That's for onto. But for one-to-oneness, we have to have enough elements in B that each element in A can have its own private partner over here. So um, the obvious, solution here is that we can just send, you know, 1 to A and 2 to B and 3 to C and 4 to D and 5 to E. And let's just write that down. In fact, you know something? I'm kind of tired, so I'm actually going to just show you this page of notes. This is the obvious one-to-one onto function. Of course, there are lots of other ones. You could send 1 to E and 2 to D and 3 to C and 4 to B and 5 to A, or, I mean, it's permutation. I'm so sorry about not feeling well enough to get you your counting video up yet. I just haven't felt well. But but there's a way to count how many of these are possible. Okay. Order actually matters. It's actually 5 factorial. You have 5 choices for places to send one. You could send it to A, B, C, D, or E. But then when you get to 2, if you want to be one-to-one and onto, you can't send it to wherever you sent 1. So there's 4 choices to send 2, times 3 choices to send 3, because you can't send 3 to any of the 2 places you sent 1 and 2. There's 2 places left to send 4, 2 elements to map it to. And then 5, by the time you get to 5, there's only 1 element left. So it's 5 choices times 4 choices times 3 choices times 2 choices times 1 choice, or 5 factorial different functions from A to B that are one-to-one and onto. Another way to understand what's required for F from A to B to be onto and one-to-one, just wanted to reword this for you. F is onto if every element Y in B gets hit at least once by an arrow coming from A. So if you drew a picture, everything in B is going to get hit by at least one arrow. It's okay for more than one arrow to hit a Y in B. That doesn't violate onto, but every Y in B needs to get hit by an arrow. It needs to be the image of at least one element in A. And F is one-to-one if every element Y and B gets hit at most once by an arrow coming from A. You can't have something getting hit by 2 arrows. It's okay for an element of B to not get hit at all. You just can't have it get hit more than once. So every Y and B is the image of at most one element in A. So if you put together at least, every Y and B is the image of at least one element X from A, and every Y and B is the image of at most one element X in A. A function F is onto and one-to-one if every Y in the codomain is the image of exactly one element X from A. And for finite sets, that forces the sets to be the same size. So I'm leaving you with a do later, but I'll sit here and talk to you about it for a while as you work on it. And the do later is just to practice these one-to-one and onto concepts. I'm going to just raise this up so you can see a little more. All right, so I'd like for you to still be able to see. All right, so here's the X and here's the Y. I've changed our sets just a little bit. X has got 1, 2, 3, 4, and 5. Y has X, Y, Z, W, T, and V. So Y has 6 elements. Part A, is it possible to construct a function F from X to Y that is onto, and if so, construct such a function? If not, explain why not. Is it possible to construct a function G from X to Y that is one-to-one? If so, construct such a G, but if not, explain why not. So I'm asking, can you build an onto function from X to Y? Can you build a one-to-one function from X to Y? And then to complete this do later, I want you to play the game in the other direction, going from Y to X. Is it possible to construct a function, say H, from Y going back to X that is onto. Is it possible to construct a function, say K, from Y to X that is one-to-one? So this should give you lots of practice. Plus, there's a worksheet in the good stuff folder, okay, for you to work on. But I'm going to give you a chance to take a note of these four four parts of this example so that you can work on this for a while, and I will stick around and visit and talk with anybody. You can chat to me privately, or you can mic in, or you can chat publicly as you work on these. And I do have complete solutions posted in the class notes that are posted, but this is a really good time for you to practice and have me around to answer questions. You can draw pictures, and if you're getting this idea about what's really going on with these finite sets, this won't be too difficult. Oh, I've already got the answer to A, because this is a situation where the size of the domain is too small. That's what Edwin said a minute ago. We can't build an onto function from a set that only has 5 elements to a set with 6 elements, because we only have 5 arrows. Each element of the domain only gets 1 arrow, right? So we only have 5 arrows shooting at the codomain. There's no way we can hit every single element of the codomain because it's got 6 elements. So you cannot build an onto function from X to Y. But what about the other way? Could we build an onto function from Y to X?
Yes.
Okay. And what would you have to make sure that you do when you're building such a function from Y to X for it to be onto?
There's enough there's enough Y's for that for there to show all X's.
Yeah, you have to make sure you hit every single element in X and you've got extras, right? So a couple of these elements from Y are going to hit the same element over here. You just got to make sure you hit every single element in X if you're trying to go the other way. All right, now let's play the one-to-one game. Is it possible to build a one-to-one function from X to Y? Shall we review the definition of one-to-one? Here's our 2 definitions, our intuitions about F is one-to-one if every element Y in the codomain B gets hit at most once by an arrow coming from the domain A. So every Y in B is the image of at most one element from domain A. So if we're going from X to Y, can we build a one-to-one function F where each element over here in Y gets hit by at most one arrow? Yeah, we sure can, Ronnie, because we have enough elements over here to handle 5 different arrows coming out of X without anything from the codomain getting hit by 2 arrows. I mean, there are lots of functions that would have 2 arrows hitting a particular element, but those would not be one-to-one, would they? What about going the other way? Is it possible? Is it possible to build a function from Y to X that is one-to-one?
Yeah.
What'd you say?
Yeah.
Okay, tell me how to build a one-to-one function from Y to X.
Hmm. Couldn't you take 5 elements from Y and put them with 5 elements from X?
You can't leave any element from Y behind. That's part of the definition of function. If Y is the domain, so glad we're having this discussion. Every single element of the domain has to map somewhere into the codomain. You can't leave anything behind. But there is an idea of like leaving some elements behind in the domain. That's called a restricted domain. And you may have even seen a restricted domain situation. There is such a thing as restricting the domain, but we're not allowed to do that here. We have to build a bona fide function from Y to X. That means each element from Y has one arrow that has to go into X if it's going to be a function from Y to X. So Ronnie's saying, no, we can't do it. Do you see now why we cannot build a one-to-one function from Y to X? Folks, does everybody understand? We got 6 arrows coming out of Y, right? There's 6 of them, one for each element of Y. They got to hit in here. Something, by the pigeonhole principle, something in X is going to get hit more than once. There's just not enough elements in X to handle 6 arrows without something getting hit at least twice. Okay, so see if you can, you know, go ahead, and take some time and write up your answers to these 4 questions. How do you explain? How do you use your own words to explain why it may not be possible to do? Well, for 2 of these are yeses and 2 of these are nos. And if it is possible, go ahead and build your own function to show that it's possible. And I will now pause. I'm going to pause the recording just so there's not a lot of dead time, but I'm not going to stop it. I'm just going to pause.